Hey y'all, welcome to gas law calculations. In gas laws, there's a lot of different variables going on. And so if we just combine all those variables and mush them together, we can get this thing called combined gas law. And this is just a variation of combined gas law. So let's go ahead and break this down. So combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. So there's a lot of different stuff. I like to just call it pivnats. So in pivnats, it's not really what I say, but P is for pressure and the units for pressure. Some units for pressure, atmospheres, millimeters of mercury, kilopascals, torr, psi. And then V is for volume and some units for volume, milliliters, liters, cubic centimeters. N is going to be number of particles. So this is just an amount, so it's just an amount of stuff. There's no technical unit for it. T, temperature. So some units of temperature that you'll see is degrees Celsius or this thing called Kelvin. So gas laws are the way the equations are set up. It's to be based on Kelvin. And the reason for this is, so Kelvin, if you've heard of absolute zero, at absolute zero, motion just stops. So just what I just did. So Kelvin's based on that. So our gas laws are going to be based on that as well. And so Kelvin, to get to Kelvin, you just add this number 273 if you're given degrees Celsius. All right, so let's go and take a look at a problem. Gas has a pressure of 655 kPa at 227 degrees Celsius. What will its pressure be at 27 degrees Celsius if the volume and number of particles do not change? And we are looking for pressure. So I'm going to go ahead and box what I'm looking for. And I just underlined different variables that or different numbers they gave me. So let's go ahead and label these numbers up. So 655 kPa, kilopascals. That's a unit for, unit for pressure. So we're going to label that as pressure. And 227 degrees Celsius, that's a unit for temperature. So we have a temperature here. And then we have a new temperature over here. All right, so we have some pressures, some temperatures, if the volume and number of particles do not change. Let's go ahead and just write down our combined gas law. So we have P1 V1 over N1 T1 equals P2 V2 over N2 T2. All right. So sometimes conditions, some stuff staying the same. So if something's staying the same, that's constant, right? So if we have two things and they're on opposite sides and they're staying constant or the same, we can cancel them out. So we have volume. So we can cancel out our V1, V2. And we also have number of particles, so we can cancel out N1, N2. So in this problem, we're looking at just pressure and temperature. So we have P1 over T1 equals P2 over T2. So our initial stuff. So 1 is just standing for initial. So anytime we want to know our initial conditions before we make some changes. After stuff is changed, that's our final conditions, which is going to be our 2's. So we're going to compare our initial conditions to final conditions. So in our initial pressure, our gas was at first at a pressure of 655 kilopascals. And our initial temperature was 227 degrees Celsius. So I'm going to write that down. No, I'm not. Why not? Right? So degrees Celsius. So degrees Celsius, we want our unit for temperature in gas laws to be Kelvin. So to change that, we got T1 is 227 degrees Celsius. We're going to add that magic number 273 to it. So if we toss that in our calculator, blah, 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 we're going to get this number 500 Kelvin, right? So we can put 500 Kelvin into T1. And then P2, our new pressure, we don't know what that's going to be. So that's going to be P2. That's our variable we're looking for. And our second temperature, 27 degrees Celsius, I'm not going to write that down either, right? So T2, if I want to get my second temperature, what number are we going to add to T2? Yeah, that's right, 273. All right, so we're going to write 27 plus 273, and that's going to give us 300 Kelvin. So now we can plug in 300K or 300 Kelvin for our second temperature. All right, so in math class, right? So if you see this, there's different ways to solve for it. You could multiply both sides by 300K and get rid of 300K and then just do math from there. You could also cross multiply. I'm going to show the cross multiplication way, but in the video I'll link over here would be the alternative way of doing it. So I'm going to change colors over here. Let's go ahead and change to red. So if I'm cross multiplying, I'm taking these two numbers here. So I'm taking 655 times 300. So I get 196,196,500. And my units are still there because they didn't cancel out. Kilopascals times Kelvin. Just put in parentheses. And what's that going to equal? It's going to equal 500K times P2. Yeah, let's go and change colors one more time here. So we got 500. Oh, that's a lovely looking 5. K, P2. All right, if I want to isolate my variable, right? So isolating my variable, I want to get P2 by itself. So what do I want to divide both sides by? I want to divide both sides by 500 Kelvin to get rid of, or to isolate P2 by itself, right? So on this side, 500K is just going to cancel out with 500K. My Kelvin on my other side is going to cancel out with that Kelvin. So our K's are gone there. And now we're just going to take 196,500 divided by 500. So we get 393. The unit we're left over with is kPa. So I'm going to toss kPa there. And that's going to equal our second pressure, our new pressure. So our new pressure is 393 kilopascals. Does that make sense? Our initial temperature was 227 degrees Celsius. So that's super hot. And it cooled down to 27 degrees Celsius. So it went from 227 to 27. As something cools down, we know that particle speeds start to slow down, right? So if the speed is slowing down, now they're not hitting those sides as much. Since it's not hitting the sides as much of the container or whatever is containing it, it's going to exert a smaller pressure or lower pressure. So that answer is going to make sense. That's why our pressure dropped from 655 kPa to 393. Let's go and jump over to problem number 2. Problem number 2. A gas occupies a volume of 180 milliliters at 308 Kelvin and 0.947 atm. What is the volume of the gas at conditions of STP? All right, so let's go ahead and write down our equation again. So we got P1, V1 over N1, T1 equals P2, V2 over N2, T2. All right, cool. So let's see if anything's staying constant. So it doesn't mention anything. And they also don't mention that we're removing gas or adding gas, or that our gas particles are changing at all. They don't mention that in the problem. So N1 and N2, we're going to cancel those out. So because we don't see particles seeping out or anything like that, or losing them in some way. And this is the variation you're going to see combined gas law most of the time. P1, V1 over T1 equals P2, V2 over T2. So let's go ahead and plug some numbers in. Pressure 1. So if we go back to our problem, let's do that first, right? So 180 milliliters. Milliliters is a unit for volume. Let's label that guy volume. 308 Kelvin. Let's go ahead and name Kelvin, remember, unit for temperature. So that's our T. 0.947 atm, so atmosphere. So that's going to be a unit for pressure. So initial pressure is 0.947 atm. And my initial volume is 180 milliliters. 180 milliliters. And temperature, 308 Kelvin. Do we have to add that 273? No, we don't, right? So it's already in Kelvin. We don't have to add it again. That's already added in for us. So 308 Kelvin. All right, we're looking for volume 2. So that's going to be our variable that's missing, right? So we're missing V2. But they also don't give us a new pressure or a new temperature. But they did tell us these new conditions are at STP. What STP is? Hey, STP is standard temperature pressure. So it's always going to be this 1 atm and 273 Kelvin. So we can plug in 273 K for our temperature. We can also plug in 1 atmosphere for our pressure. And if you notice, our initial pressure is 0.947 atm. So we just want to make sure that our units are matching up on both sides. So we can use that 1 atm. If it didn't, then we just have to convert over to whatever unit of pressure we were in, or whatever pressure we were in initially. So let's go ahead and look at these numbers. A lot of things happening on the screen. Let's go ahead and multiply 0.947 times 180 just to get that number to be a bit smaller here. So kind of simplify it down. We got 170.46, thanks to my handy dandy calculator, ATM times milliliters over 308K. Oh, my K's are looking great. And then 1 times V2 is just going to be V2. And 273K. All right, from here we can just cross multiply, just like last time. Again, different variations, different stuff you can do. So I'm just going to take 170.46 times 273. Whew, that's going to give me a big number. So I'm multiplying this and this. And so I'm going to get 46,535.58. If I want to toss my units on there, that's ATM times milliliters times Kelvin. I'm not going to for space wise for right now. And that's going to equal, I'm going to change colors here to green. And we're going to take 308 times V2 to be on our other side. So we got 308 V2. All right, so if we want to isolate our variable, we're going to divide both sides by 308. So I'm taking 46,535.58 divided by 308. And I got 151. That's going to equal our V2. And since this is our second volume, right, our initial volume over there was milliliters. So what do you think this final volume's unit is going to be? Yeah, it's going to be milliliters too. So our final volume is 150 milliliters. If we look back at our units too, we're going to end up, let me switch colors here. We're going to end up, ATM is going to cancel out, the Kelvin is going to get canceled out, and we're going to be left with those milliliters. So our final answer for this one is 150 milliliters. We started off at 180 milliliters at a temperature of 308K. What happened to our temperature? Our temperature dropped. It dropped to 273. So if our temperature is dropping, now our particles are moving slower. So if our particles are moving slower, and if the volume is not fixed, they're not going to be hitting those sides anymore, and they're going to start to come closer together. And as they're coming closer together, the pressure is going to increase, or at least in this case, our pressure is increasing as well, 0.947 atm to 1 atm. So there's a lot of different things going on here. But 150 milliliters is our final or our new volume. All right. Pause the video and try these two problems. So best of luck on it. You guys got this. I'm going to go ahead and move this over here so you can see it. So pause the video. Try these two problems. Okay. All right. So hopefully you did pause the video and you tried these two problems. So for this first one, our new pressure should have been 23.6 psi. 23.6 psi. And for problem number 2, what's the volume of the gas? This is where we had 3 variables, and this should have been about 810 milliliters. If you didn't get either that first one or second one, definitely look back, see what you did. You may have not converted degrees Celsius to Kelvin, right, in that second problem. That would, I feel like, would be the most common mistake. But if you guys need extra help, take a look at those links that I attached. All right.